Welcome everybody to section 4.5, integration by substitution, or what I like to call u-Substitution. So to get into it, let's take a couple of derivatives using the chain rule. Okay, so suppose we have this capital F of x function equal to 1/3 the quantity x squared plus 1 cubed. Find f prime of x. Okay, so granted this quantity is being raised to a power, so we're looking at the chain rule here. So the derivative, if I bring down the 3, those will cancel, and we'll get x squared plus 1 to the second times the derivative of the inside. So we could write this as 2x quantity x squared plus 1 to the second. So look, if we can take the derivative of f and get to this, if we were to integrate this guy, it should take us back to that original function, okay, with perhaps a plus c added to it. A little more abstractly, suppose we have a composition of functions, f of g of x, and we look to take the derivative of that. So that's what that's saying. Take the derivative with respect to x of the composition f of g of x. This is precisely where we use the chain rule when we have a composition of functions. The outer function is f. This would become big F prime, leave the inside function alone, times now the derivative of the inner function. Okay, and we can look at it like that. And again, sometimes we let the derivative of big F be notated by little f, so I could write it like this, little f of g of x times g prime of x. So again, taking the derivative of big F of g of x using the chain rule, we get little f of g of x times g prime of x. So again, the point being then, if I have something of this form inside of the integral, it should take me back to this big F of g of x function, okay? And so this is what u-Substitution is for. It's for really using, it's for integrating basically the result of the chain rule, okay? So I kind of call it the all-encompassing power quotient chain rule for integrals, but really it's the result of chain rule. And here's how it works, okay? So suppose we have something of the form f of g of x, g prime of x, and we want to integrate that, okay? So here I'm saying let the derivative of big F be little f. So we can notate, if we take the derivative of big F, we can use a little f to notate that. So look, I want to integrate little f of g of x times g prime of x. This is why it's called u-Substitution. We're going to let u be this inner function of x. So off on the side, I'm going to let u equal g of x. What I'm then going to do is I'm going to take the derivative of both sides with respect to x. So du over dx on the left. On the right, I'll write it as g prime of x. And what I really want to do is get all the u stuff alone and all the x stuff alone. So what I'm actually going to do is I'm going to multiply both sides by dx here to get du alone. And we see that du is equal to g prime of x dx. Now what we're going to do is some substitution. G of x becomes the letter u. I'm going to replace that with the letter u. Notice that du replaces g prime of x dx. That's this thing right here. That will get replaced with a du. So the new integral becomes the integral. I didn't do anything with the letter f. That stays, but the g of x becomes the letter u, and all this g prime of x dx became our du. And with a little bit of substitution, letting u be the inner quantity, we have now rewritten this integral from one that's ugly and in terms of x to one that's pretty nice now in terms of u. This is no longer a composition. This is something that I can integrate. If I integrate little f function, it takes me back to the big F function. So this gives me back big F of u plus my constant. And then I replace u with what it originally equaled, which is g of x. And I get back capital F of g of x plus c. And this is the result of u-Substitution. And by the way, this was our second warm-up problem. When we took the derivative of big F of g of x, we got back little f of g of x, g prime of x. This is how we work backwards now, okay, through u-Substitution. So let's do a bunch of examples and start getting a feel for this stuff, okay? So the rest of this lesson, bunch of examples, take your time, go through it. When you feel confident, start pausing and trying them on your own, hitting play, and then seeing how you did, okay? But let's go through the first couple together here. And again, part of it is really recognizing what to do. So the idea with this notation, by the way, is like we have some sort of a product or quotient going on if you think about it. We've got like this thing times this other thing. And the key is that we're basically multiplying by the derivative of the inner function, all right? So let's start with some quantities raised to powers. That's usually the easiest kind of u-sub problem here. So looking at this one in gray, okay, we have 2x times the integral of x squared plus 1 quantity squared. That was actually our first warm-up problem. So I'm expecting to get back like this 1/3 x squared plus 1 cubed, perhaps with a plus c. All right, so how does it work? Well, if you think about it, anything in the parentheses is like your inner function. This is like my g of x up above. This is what I'm going to call the u portion, the inner quantity. U is going to be x squared plus 1. Then I take the derivative. So du over dx is going to equal 2x. And then I'm always going to multiply the dx back to the right-hand side with the x stuff. So you're rarely going to see me actually write this. From now on, you're probably going to see me write it like this with the dx on the right-hand side, okay? But this is always the start. Figure out what your u is, okay? I'll circle that. That was this thing. Then you look at your du, and you look at what's left in terms of x in the integral. I have a 2x dx still to take care of. That is precisely what's going to get picked up with the du here. So rewriting this becomes, okay, so again, this thing that I've circled is my u. I'm going to replace that with the letter u, and it looks like I'm squaring it. So I have a u squared. My 2x dx is exactly equal to a du. So this is the new integral I get back. Integrating with respect to u, I'm going to get u cubed over 3 plus c, or 1/3 u cubed plus c. And then replacing u with what it equaled at the end of the day, back in terms of x. And sure enough, that's basically exactly what we started with in the first warm-up problem, with the exception of the vertical shift of plus c. Okay, but we did get that 1/3 x cubed plus 1, x squared plus 1 quantity cubed back. Okay, so this is the idea. So the trick is realizing what are we going to let u equal, and then we got to make sure the du is picking up the rest of the x stuff. All right, so let's go through some examples here. See how this stuff goes. Okay, in the next example, the integral of 3x squared times the square root of x cubed plus 2. So again, I mean, if you think about it, we do have a quantity raised to a power here. I can think of this as the quantity x cubed plus 2 to the 1/2. So I'm going to let this inner portion be my u. I'm going to let u equal x cubed plus 2. So du is going to be 3x squared times dx. And that's precisely what's left in the integral. So the new integral becomes, all right, so circled is my u, and that's being raised to the 1/2 power. 3x squared dx is exactly equal to du. So I now get this integral back, more or less square root of u. Integrating now. U to the 3/2 over 3/2, or in other words, 2/3 u to the 3/2 plus c. Replace u with what it originally equaled, in this case x cubed plus 2. And there's your antiderivative. And by the way, what could you do if you wanted to check your answer? You can always turn around and take the derivative here. If I take the derivative of this thing, using the chain rule, I bring that power down. Those are going to cancel because the reciprocals. I'll get x cubed plus 2 to the 1/2 times the derivative of the inside, which is 3x squared. That's exactly what I started with inside the integral, so I know I've done it correctly. Okay. So if you want, you can try this one on your own, see how you do with it. Okay. I'm going to let u be the inner quantity. Now let's look at our du. Oop, that should be, excuse me, just x to the first out front. My apologies. That should just be an x out front. X times the square root of 2 plus x squared. So du is the inner quantity. When I take the derivative, we get back 2x times dx. You may notice there's something a little different about this example than the previous ones, in that what's left in terms of x does not exactly equal du here. We have an extra 2 in our du. But in the integral, we need to account for x dx. This is pretty common when you have a leftover coefficient. Basically, think about it. If we want to replace x dx in the integral, we're going to have to divide both sides by 2 here, or multiply both sides by 1/2. So in this case, I'm going to have an extra constant attached to my du. So the way I'm going to rewrite this integral, here's my u, which was square root of u, so I'm going to write that as u to the 1/2. X dx is equal to 1/2 of a du. And so when I'm left over with these constants, I just throw it out in front of the integral. Okay? So now I'll keep the 1/2. When I integrate u to the 1/2, u to the 3/2 over 3/2, or in other words, 2/3 u to the 3/2. I'll clean up out front, and I will replace u with what it equaled, which was 2 plus x squared in this problem. And there's our antiderivative. Okay? So again, not uncommon to have extra coefficients that you got to deal with when you go through these. Okay? Next up, we have the quantity 4x minus 7 to the 8th power that we want to integrate. Now here, it might not look like we're multiplying by much, but if you think about what we have inside here, it's a linear quantity. Let's see what happens if we let u equal that linear quantity. du is just going to be 4 times dx. Well, here's my u. I've accounted for that. It's going to be u to the 8th power, but I still have a dx to get by itself. So to get dx by itself, I will divide by 4. So I'm going to replace the dx in the integral with a 1/4 du. So again, procedurally, I usually start with my u. This is my u, which is being raised to the 8th power. dx became 1/4 du. Now I'm ready to integrate. I keep the coefficient. U to the 8th will become u to the 9th over 9. So we'll have 1/36 of 4x minus 7 to the 9th plus c. So this technique is great when you have a linear quantity raised to a power. Okay, it will always work for that. All right. If you want, give the next one a try, and we'll do a couple more of these, and we'll take a look at some bounded ones coming up shortly after we get through the next 4 examples. And then after that, we'll do some trig ones, okay? So again, if you need to take a break through the lesson, please do so, but we'll go through a bunch of examples here, okay? So again, we have a quantity raised to the negative 1/2 power. So I'm going to let u be that inner quantity. du is going to be 4x cubed dx. As I look at the original integral, I do have x cubed times dx to account for. So again, I will divide by 4 and get a 1/4 du. Rewriting this, it looks like I have u in the denominator under the radical. That took care of the bottom. X cubed dx, which is left, is my 1/4 du. Now, sometimes you'll see a du or a dx in the numerator. What that really means is it's 1 over, okay? So, like, I could write this either way here. But I just want you to be aware that sometimes if there's a 1 in the numerator, that du or dx or whatever it may be is going to be up there, okay? Any event, I want to rewrite this with the appropriate power, which is the negative 1/2 power, radical in the denominator, and now we're good to go. Keep the coefficient. U to the 1/2 becomes u to the negative 1/2. Add 1, we get positive 1/2 divided by 1/2, or in other words, times 2. Out front, we have 2 over 4, which is 1/2, replacing u to the 1/2 plus c. All right, so I just cleaned it up. Oh, that should not be a quarter out front. That should be 1/2. I didn't clean that up very good. But yeah, 2 over 4, 1/2. Okay. Next up, we've got the integral of 12x squared over quantity 2x to the 3rd minus 1 to the 5th. What are you thinking for u? If you're thinking this quantity in the denominator, you are correct. Taking the derivative, we're going to get a 6x squared dx. Now, look, we want a 6x squared dx. The integral has a 12x squared dx. Think about how many du you're going to need. Some of you are saying 2. You're probably right. Here's something else you can do, like if you get tricky with the coefficients. Here's a coefficient. I can move that out front to begin with if I want. Okay? And what I can now do is say, look, here's my u. In the integral, I have x squared dx to take care of. There it is. That's going to be a 1/6 of a du. So I can actually leave the original coefficient there. I can replace my denominator with u to the 5th, and then my x squared dx became a 1/6 du. Looks ugly, but we can clean this right up. What's 1/6 of 12? Put those together, you get a 2. I can write this as 2 integral x to the negative 5th du. Okay? But again, I mean, if you realized right away that if I want, you know, a 12 out of this, I would have to multiply both sides by u. You don't have to separate things like I did, but if you find it helpful to do it that way, then do it, okay? But in any event, it's going to take a little practice typically to get this down, and once you get it down, you'll be good, okay? Integrating x to the negative 5th, x to the negative 4 over negative 4. 2 over negative 4 out front is again a negative 1/2. U 2x cubed minus 1 to the negative 4th. You can leave it like that if you want. You can write it as negative 1 over 2 and then this quantity to the 4th in the denominator. Either way. All right, but again, take your time, pick U, find your du, match it all up. Okay. All right, next one. A little trickier, the next two examples here. If you notice about all the previous examples, we had like, you know, everything was like one term was 1 power higher than another. Like we had 2x cubed here, we had an x squared to go with it. So, I mean, if we take the derivative of something with x cubed, we get back something with x squared. If we take the derivative of something with x to the 4th, we get back something x cubed. If we took the derivative of this linear thing, we get back something with a constant. When we took the derivative of this x squared, we got something back with x to the 1st. So what's a little different about the next example is that, well, you notice it's x plus 1 under the radical. It's also x to the 1st outside of the radical. So like this, if it was x squared plus 1, would look a lot more like the ones we've been doing, okay? So look, let's take a look at this particular example here, okay? One thing you will never do is let u just equal x. You might be like, all right, let me let u equal that x. Think about what happens if you do that. Then du is just 1 dx. So I can replace that with a du, but I've also got that u to take care of, or that x. Well, all letter x's can be replaced with the letter u. If I do that, you know, I basically get back exactly what I started with in terms of u, just not in terms of x. It's exactly the same integral. Letting u equal x will never do anything for us, okay? So we don't want to do that. All right, so that's a big hint. So there's really only one other thing u could equal here, and that's the quantity x plus 1. Let's see what happens. If I let u equal x plus 1, then du again is just 1 dx here, and I can pick up that. I've still got that x out front to take care of. Now we go back to the u equation and solve for x in terms of u. If u is equal to x plus 1, then x by itself would be what? U minus 1. That's what I'm going to sub in for the first term here. So the x that's underlined double becomes u minus 1. This is the square root of u, and then my dx was just a du. And we get back this integral. Now it's still a product, and we can't integrate, but what we can do, unlike with the original one, is we can now distribute this radical u back through. We can't distribute the x into a radical, that's no good, but we can distribute a radical into a quantity to the 1st power. So that's the idea here. All right, look, and in fact, I'm going to rewrite that as u to the 1/2, and now I'm going to distribute that back in. So u to the 1st times u to the 1/2, that becomes u to the 3/2 minus u to the 1/2 du after distributing. Now we can go ahead and integrate this. So just be careful adding 1, u to the 5/2, and 2/5 out front, minus u to the 3/2 with a 2/3 in front of it, and a plus c, and now just replace your u's with x plus 1, because that's what it equaled. And there's the end result. And again, if you wanted to go through the chain rule and take the derivative, you would get back exactly what we started with. You'd have to do a little bit of simplifying, but you would get that. Okay, and then this example is again similar, but notice we do have an x squared here. If you let u be x squared, because you're thinking, oh, the first derivative will pick up x to the 1st, be careful. U sub can get tricky. All right, we get that. So look, here's my u. This has x times dx in it. I can move the 2 over, that's no problem. But I do not have an x times dx left to pick that up. The du does not match with what's here. I don't have x times dx left. All right, and so this doesn't work. We're not going to let u equal x squared. It's not going to help us here. Let's instead let u equal the quantity. Du then becomes 1 dx. We can pick that up. But now, again, we have this x squared to account for. So, again, we're going to come back to u, and we're going to get x by itself. That would be u minus 1. And now what do you suppose we're going to do to it? We're going to square it. And there's what x squared can get replaced with. So from left to right, x squared becomes quantity u minus 1 squared. Now we've got the square root of u, and then our dx became du. Again, we've got that to square out, and we've got that to distribute through before we can really integrate this thing. So again, you kind of got to recognize the need to do those things. Squaring, I'm going to get u squared minus 2u plus 1 times u to the 1/2. Distributing the u to the 1/2 through, we're going to end up with integral. 2.5 is 5/2 minus 2u to the 3/2 plus u to the 1/2. And now we can again integrate this thing. So we're going to get u to the 7/2 with 2/7 in front, minus, keep the 2, u to the 5/2 with a 2/5 in front of it, plus u to the 3/2 with a 2/3 in front of it, plus c. And now replacing our u's. 2/7 quantity, 1 plus x to the 7/2, minus, that will become 4/5, 1 plus x to the 5/2, plus 2/3 of 1 plus x to the 3/2 plus c. And there's the final result. All right, now let's do some that are bounded and see how this stuff works. Now we're specifically looking for the area under this function from 0 to 1. Again, we've got a product, we've got a quantity raised to a power. We should be thinking u-substitution here, okay? Quantity being raised to the power, let's let that be our u. du becomes 3x squared dx. Looking at the integral, I have x squared dx. I can account for that with a 1/3 du. Now look, these are called x bounds. Okay? What is the area under this graph of x as x goes from 0 to 1? Well, now we're turning it into an integral of a different letter u. Drop the bounds. Basically, this is going to become the integral. Let's start with the u stuff. U is our quantity being raised to the 4th. X squared dx became a 1/3 du. What I'm not going to do is replace the x bounds of 0 and 1. I can write this as x goes from 0 and x goes to 1. But I'm not going to sub those in for u. So I'm going to leave those in terms of x. Now look, I'm going to keep the 1/3. I'm going to integrate. And we're going to get what? 1/5 u to the 5th back as x goes from 0 to 1. Remember, it's bounded, so we don't need the plus c. And now I'm going to clean up the front and replace the u. So basically 1/15 and u was x cubed plus 1. And that's now to the 5th. Now I can don't have to write the x equals. We write the bounds in terms of x again. And now we can evaluate. All right. So plugging in the upper bound and plugging in the lower bound. Let's see, we're going to get 1/15, it looks like, of 2 to the 5th minus 1/15 of 1 to the 5th is 32/15 minus 1/15 is 31/15 at the end of the day. Okay, so this was the technique where it's called replacing the bounds. We remove the bounds more or less, keep them in terms of x, and then replace them at the end. This is the only time you're going to see me do it this way. All right, I'm going to show you this again, but we're going to do a technique called change of bounds, which is common on the AP exam. They can find ways to test your knowledge about that, so you want to know it. Okay, so basically, to get rid of all this, we're still going to get the same exact end result back here, but here's how change of bounds works. Doesn't affect our u. We got the same u. We got the same exact du here. Okay, x squared dx is 1/3 du. Here's how change of bounds works. We're literally going to go from x bounds to u bounds here. Basically, what we need to do is figure out what does u equal when x equals 0, what does u equal when x equals 1. So we use our u equation of it. When I plug 1 in for x, that's the upper bound, what does u equal? Looks like that equals 2. When I plug the lower bound in for x and plug it into my equation for u, it looks like the lower bound becomes 1. Now what I'm going to have is an integral that goes from 1 to 2, u to the 4th. That was my 1/3 du. All that's the same, but now we've got these u bounds, okay? So when I integrate, I no longer replace in terms of x. I finish this problem out in terms of u. And it shouldn't take you long to realize, yeah, we're getting exactly the same thing back here. With honestly a little bit of a time saver. By changing the bounds, it saves us from having to replace everything in terms of x at the end. and they will again test you on the AP exam. You know how they do that is they'll say, like, here's this integral. If you let u equal x cubed plus 1, which of the following integrals would be equivalent, all right? And they would have this as one of the answer choices, but I guarantee you they'd also have this as one of the answer choices because it's the easy mistake not changing the bounds over, okay? So you definitely want to know the technique of changing bounds. Let's do another one, okay? Integral from -1 to 0 of x squared over the square root of x cubed plus 2. All right. And so again, we've got this inner quantity. I'll let u equal that. The derivative is going to be 3x squared dx. Well, I have an x squared dx, so I'll pick up 1/3 of that. And then for my bounds, if I plug 0 in for x, it looks like the upper bound is 2. If I plug -1 in for x, -1 cubed is -1, plus 2 is +1. So we still end up with some nice bounds, 1 to 2 here. So let's see, this becomes the integral from 1 to 2 now. I have u in the denominator under a radical. X squared dx was 1/3 du. So I'm going to take a moment to rewrite this as u to the -1/2. And now we're good to go. So keep the third. When I integrate the -1/2 power, I get back +1/2 over a half, or times 2. And now we're evaluating in terms of u from 1 to 2. So, looks like out front we have 2/3, and then I'm going to have 2 to the 1/2 minus 2/3 of 1 to the 1/2. So that becomes 2 radical 2 over 3 minus 2 over 3, or 2 radical 2 minus 2 all over 3 at the end of the day. And if you'd rather go and replace everything in terms of x, plug in the -1 and the 0, you should get the same end result here. Okay, so watch for the change of bounds. And now let's do a few trig ones, right? And again, the better you are with your trig derivatives, the easier u-sub with trig will be, okay? So again, let's start with a couple where trig functions are raised to powers. And let's remember, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is secant tangent, okay? So we're going to focus on those today. So for the first one, we have the integral of sine squared x times cosine of x dx, okay? And again, if you're thinking along the same lines for now, let's try letting u be the trig function with the higher power. If we let u equal sine of x, what's the derivative? Well, that's going to be cosine of x times dx. And that I can pick up. It looks like we chose u correctly, okay? So u was sine, that's being squared here. Cosine x dx is my du. This will become 1/3 u cubed plus c, and then subbing back in for u, we get 1/3 sine cubed x plus c. Go ahead, take the derivative. If you do, you use the chain. Well, the 3 swings down and cancels. Sine squared x times the derivative of sine, which is cosine, exactly what we started with inside the integral. Okay, let's see what happens if you chose the incorrect u for this, by the way. So again, just to kind of show you, if we had sine squared x cos x dx, and you said, well, let me let u equal cosine here. And then du is negative sine x dx. There's my u. I can get a sine of x times dx out of this by moving the negative over on that side, but I don't have sine x times x. I have sine squared x dx. And there's no way I can take negative du and make that just a sine squared x. If I want to square that, I have to square everything. And you're never going to square your dx's in an integral. It doesn't really make sense. Dx represents the very thin width of the rectangle. We don't square those. So that tells me if I let u equal cosine, I'm not going to have a du that's going to match up with what's left in the integral. This isn't going to work. So sometimes, you know, it can be tricky to pick out your u, so you want to be careful. All right, let's try a bounded one. It's pretty similar to the first. I've got cosine of the 4th theta, sine theta d theta. I want the area under that from 0 to pi over 2, okay? So again, cosine's the one with the higher power here, so I might think to let that equal u, cosine theta this time. Du would be negative sine theta d theta. Well, I can get that positive by multiplying both sides by -1. Now I want to change my bounds. U of pi over 2 here would be cosine of pi over 2. I just plugged that in for theta. And the cosine of pi over 2 is 0. u of 0 is going to be the cosine of 0, which actually equals 1 here. So now, notice the lower bound is 1, the upper bound is 0. This is my u to the 4th. Sine theta d theta, negative du. You can go ahead and work this out if you want. I don't like when the larger bound is on the bottom. Okay, notice the bigger bound is down below and the smaller bound is up top. I'm going to apply a principle of integration that allows me to flip the bounds. And what do I have to multiply when I flip the bounds? -1. To me, that's pretty convenient. This will come back the positive integral 0 to 1 of u to the 4th. Okay, and so now I'm going to get 1/5 u to the 5th plus, no plus c because it's bounded. And so we get, let's see, 1/5 of 1 to the 5th minus 1/5 of 0 to the 5th should just equal 1/5 at the end of the day. All right, so if you graph this on your calculator from 0 to pi over 2, probably not going to see too big of a region above the x-axis, but it would be an area of 1/5 if you did. Okay? Okay, next up, another bounded one. Here's just sine of t times cosine of t dt from pi over 4 to pi over 2. Well, sine and cosine are derivatives of each other. Notice neither of them really has a power here other than the first power. Let's see what happens if we let u equal sine of t. du will be cosine of t dt. So that looks pretty good. That picks everything up. Changing the bounds. Sine of pi over 2 is 1. And the sine of pi over 4 is radical 2 over 2. So there's our bounds. This becomes now the integral from radical 2 over 2 to 1. That was my u. That was my du. Integrating 1/2 u squared from radical 2 over 2 to 1. Evaluating 1/2 of 1 squared minus 1/2 of radical 2 over 2 squared. So it looks like first term is going to be 1/2. Second term, let's see, if I square this, I get 2 over 4, which is 1/2, times the other half in front of it, so 1/4. And so it looks like at the end of the day we get back exactly 1/4 unit of area. Okay, that's letting u equal sine. Well, let's do it again, but this time let's let u equal cosine and see what happens. Because maybe you were thinking along those lines. So what was our answer? 1/4. Let's see what happens now if we let u equal cosine of t. Maybe you saw it that way. Well, look, I'm going to let u equal cosine of t. Then du will be negative sine t dt. Well, I can pick up sine t dt with a negative du here. Okay, changing the bounds. Cosine of pi over 2 is 0. Cosine of pi over 4 is radical 2 over 2. Okay, so now I have a lower bound of radical 2 over 2 and an upper bound of 0. Cosine is my u, sine t dt was my negative du. Once again, my larger bound is in the bottom, so I'm going to flip and negate. This becomes positive integral 0 to radical 2 over 2 of u du. So we get 1/2 u squared back, evaluated from 0 to radical 2 over 2. And we're going to have 1/2 times 1/2 again for an end result exactly the same as when we first did it, 1/4. So in this example, you know, there were 2 different ways to go through it. That's not always going to be the case. Usually there's one specific choice of u that'll make it work. Rarely, like in situations like this, it could actually work out either way. Okay. Next up, we'll focus on some tangent ones. Remember, the derivative of tan is secant squared, right? So if you see tan with a secant squared, usually the tan function is going to be your u, and the du will pick up the secant squared. So here we have the integral of tan to the 5th secant squared x dx. So again, let me let u be the tan function, du here secant squared x dx. That's exactly what we have here, okay? So that's going to work. This becomes now u to the 5th du. 1/6 u to the 6th plus c when we integrate. 1/6 tangent to the 6th power of x plus c. And that's it. You're done. All right. Next up, integral of tan theta secant squared theta d theta. Okay? Look, even though secant's the one with the power, you can let u be tangent because, again, du will pick up the secant squared. So again, with these trig ones, it's not always going to be the trig function that has the highest power. That's usually a good place to start. But again, the better you know your trig derivatives, the easier u substitution with trigonometry is going to be. U equals tan theta. The derivative is still secant squared theta d theta, which is exactly what we've got here. Becomes the integral of u, and then du, 1/2 u squared plus c, 1/2 tangent squared theta plus c. Okay? Now, if you're really good, you could let u equal secant theta, and that would work here, just to kind of show you. Let me expand this out. Tan theta times secant squared theta. Well, I could write that as secant theta. If I let u equal one of the secant thetas, let me just circle this one, for instance. Du is secant theta tan theta d theta. That is all exactly what's left. That works. I can make this u for secant. All that other stuff is du. And here I get back 1/2 secant squared theta plus c as an antiderivative. Okay, so they both work, but my focus when I see tan with secant squared, I usually go this route, the first route. Okay, so here we have secant to the 5th y times tan y dy. Notice we don't have secant squared this time, so if I let u be the tangent of y, du is going to be secant squared y dy. Well, I need secant to the 5th, and again, I can't really mess with powers on the du stuff. That doesn't seem to work here. So let's try something different. What if we let u equal secant y? Then du is going to be secant y tangent y dy. Let's see if we can make this work. Okay? Let me expand this out a little bit. Remember, I want a secant y times dy for my du here. So let me think about a way I can rewrite this. I'm going to actually make this. If I break off a secant y tan y dy, what power of secant is left? Well, that's got to be what? Secant to the 4th y to get back to my original 5th power. If I want this to be my du, then this has to be my u. But think about it. Now, I've got u to what power out here? The 4th. So we got u to the 4th to pick up secant to the 4th y, and then the secant y dy got picked up with du. Okay, so a little tricky there, having to break off one term, but we got it to work. So we're going to get 1/5 u to the 5th plus c, 1/5 secant to the 5th y plus c. And again, if we want to see if this works, let's take a look. If I take the derivative of this, bring down the 5 using the chain rule, that'll cancel. I'll get secant to the 4th y times the derivative of secant, which is secant y tan y. And sure enough, secant to the 5th y tan y is exactly what we got back when we took the derivative. That's what was in the integral. Okay? And now this example, tan x over cosine squared x dx. You may be thinking, all right, cosine, it's got the power. What happens if I let u equal cosine? Well, then I get negative sine x dx back. So I could have like u squared in the denominator, but what about this negative sine x dx? Not loving it. I got the tan function up there. What if we let u instead be the tan function? Du, we saw, was secant squared x dx. I actually like that a lot. Do you? Do you see what it is I like about it? Think about what secant squared really is. Isn't secant squared really 1 over cosine squared? And so that's what we have here. This is my u in the numerator. This is my du, the 1 over cosine squared dx. This just becomes u for tan, du for the 1 over cosine squared. So once again, we're getting 1/2 u squared. We're getting 1/2 tan squared x plus c back. By the way, this is actually the same exact problem as this one right here. Okay, tan times secant squared. Okay, the one we did 2 problems ago. Okay? And then sometimes you'll have like little linear quantities inside your integrals, like with the u-subs. Let's say I have something like cosine 3 theta minus 1 d theta, right? To do these, you're going to let u be the linear quantity. We'll let u equal 3 theta minus 1. Du becomes 3 d theta. Well, there's d theta, so I'm going to pick that up with a 1/3. This becomes cosine of u. Notice I didn't do anything with that. This whole thing just becomes cosine of u. D theta became a 1/3 du. Keep the 1/3, integrate cosine to get back sine, and replace with the 3 theta minus 1 that we began with. Okay, so again, sometimes you'll see linear quantities in there. You could see something like this, say like, let's do something like twice the integral of sine to the third of, you know, let me go 4 theta minus 7 cosine 4 theta minus 7 d theta. Okay, so this is about as complex as I think it would get for now. We got to let more than u be just the 4 theta minus 7 because we have the sine times the cosine function here. Here I would let u be the sine of 4 theta minus 7. du, we got to use the chain rule. Derivative of sine is cosine 4 theta minus 7 times the derivative of the inside, which is 4. Well, I have a cosine 4 theta minus 7 there, so I'm going to bring the 1/4 over to the du side. Let's put this together slowly. Out front I have a coefficient, a constant of 2 that I'm not doing anything with. In the integral, now I'm going to have this is my u being raised to the 3rd power. This is my 1/4 du. So I'm going to put the 1/4 out front, and I can make that a 1/2 out front if I want to clean it up a little bit. And so here 1/2 times 1/4 u to the 4th, 1/8 of sine to the 4th of 4 theta minus 7 plus c. And again, with a quick check, if I take the derivative, bringing down the 4, I get 4/8 sine cubed 4 theta minus 7 times the derivative of sine, which is cosine 4 theta minus 7, times the derivative of 4 theta minus 7, which is 4. And let's see, the 4 and the 4/8 out front becomes 16 over 8, which is 2. Sine cubed of our quantity, cosine of our quantity, and that's exactly what we had up in the integral to begin with. Okay, folks, so take some time to practice this stuff. It will get tricky. It'll challenge some of you, but if you have questions, reach out, and more to come.